Okay, so we come to selection. Selection is a seriously important operation in relational databases. It's basically the main filter. So you specify a table, or in general a join, and say which tuples from that table you want to appear in the result, and obviously that's the where clause. So what you end up with, if you run a query like this, is a subset of the tuples from table R, and all of those tuples obviously satisfy that condition. Right, so this condition can have several different flavors, if you like. You can ask a condition that only involves one attribute. So select star from student where ID equals 7654321. Right, so that's a selection using a single attribute. You could also use an inequality, so select star from students where age is greater than 60, for example. So those kind of selections where there's only a single attribute in the condition, I've called one-dimensional. And queries that have multiple attributes in the where clause, I've called multi-dimensional. So these two different flavors can be handled differently depending on the context. And as we'll see, there are different file structures and different ways of using the files depending on the kind of selection that we've got. And one final style of selection is similarity matching. This is not what you find in a regular DBMS. Postgres does have one kind of similarity matching, text similarity. Of course, we all know how to build new data types and new operators, so if we really wanted to, we can implement our own similarity matching for some other data type like images or songs. All right, anyway, selection, extremely important operation in DBMSs and in relational algebra. So here diagrammatically is what we're going to discover when we run a selection clause. So some pages, the ones highlighted in red, contain matching tuples. Only some of the tuples in the page are matching. And this is a general type statement. Certain different types of queries will have perhaps have all of the tuples in a particular page matching. But in any case, so some tuples will match, and we'll call that the total number of tuples that match. We'll call RQ. And another quantity that I've already mentioned is the number of pages that contain matching tuples, and we'll call that BQ. So in this diagram here, we've got 8 matching tuples, and they are located in 5 different pages. I haven't bothered putting the links between the data pages and the overflow pages. Doesn't really matter where they go. Maybe this page here is overflow from page 0, etc., etc. But ultimately, we're going to need to check all of the relevant data pages plus their associated overflow pages in answering a query. All right, so there are different categories of selections, and I've given them names. Queries that return at most one result, I've called one-type queries. So RQ is between 0 and 1. Well, it's either 0 or 1. And BQ is either 0 and 1. So if we've got one matching tuple, it's located on one page. Whether you have to read multiple pages to find that page is a separate issue, but we know for sure one tuple will be on a single page. And the classic example of that is testing for a particular primary key value. So that example there. All right, if you want to include more attributes in the queries, then you can have partial match retrieval. And basically, all of the tests are still equality tests, but now we can have multiple attributes involved, or we could have a single attribute involved. And basically, the deal here is we don't have at most one answer. We can have every tuple in the table matching this query. Now, of course, this is pretty unlikely, but it's possible, depending on what we ask. And similarly, we'd like to get even less answers for a query like this, presumably half the number that we got with this query. So some number of matching tuples, and they will be distributed across some number of matching pages, which could include all of the data pages and all of the overflow pages. So that's the upper bound on BQ. If every tuple in the table contains at least one matching, if every page in the files contains at least one matching tuple. All right, range queries, now where we stop doing equality tests and we do inequality tests. So we're looking for age greater than 18 and age less than or equal to 21. So our age between 18 and 21. All right, so it's the fact that we're dealing with age means we're going to have multiple answers anyway, and we're likely to have quite a large number of answers in this particular range here. And similarly, that's one-dimensional because it only involves a single attribute. If we involve multiple attributes, so we're looking for people in this age range, and they must have a height in that particular range. So that's, if you like, a two-dimensional query. All right, other types of queries, we've got pattern-based queries, using, for example, like, or using Postgres's regular expressions. So we can search for tuples based on a pattern matching a text field in the tuple. So once again, if you ask a query like, name tilde XYZZY, you're likely to get 0 matching tuples. But if you ask the query where name like %, then you'd get everything as a matching tuple. So that's the range of tuples, and similarly based on that, the number of matching pages could be 0, or it could be every page in the data file. All right, and one final selection type, similarity matching. Now this is qualitatively different to the ones that we've just been looking at, because, well, for one thing, in theory, everything is a match. Because you can argue that everything is similar to some degree or other. So we need some kind of similarity measure in order to do similarity matching. Kind of makes sense, doesn't it? Typical similarity measures would have a value in the range 0 to 1, where 0 means totally different, not a match at all, so that kind of goes against what I said up there, or identical. So we've got an input, so the kind of places where this is used is matching multimedia type thing. So you can feed in a sample image and find images that are similar to that. So if you feed in a picture of sunset, then it will find images, well, it will hopefully find images that also have sunsets in them. You can see examples of this kind of thing if you do Google image search. It tries to find similar images. However, it does it by looking at the words around the image. So it's actually text-based rather than comparing image against image directly. All right, so in similarity matching, every tuple every object in the table has a similarity value compared to the query image or the query object. So what do? We can't return all our tuples, so we do a Google does. We first of all rank them according to their similarity value. So if you've got, a few images, if you keep looking at this image example, where the similarity is 0.95, 0.96, 0.98, they're pretty close. They'll be the most similar matches. And then we may have things where the similarity is 0.5 or even 0. I guess you'd get that if you had a really stupid example. An all-white image is your sample image, and somewhere in the database you've got an all-black image. I imagine that the similarity there would be 0. All right, so ranking is an important concept once we get to similarity matching. It's all very nice to rank, but if you looked at your average Google search, there are 100,000 matches. We don't want to try and look at them all, even if we rank them. So there are two possible ways you can deal with this. One way that Google uses is just to show you the top 10 items. Of course, you can page through and get the next 10 and the next 10 and the next 10 and so on. But, okay, go to the ranked list, which is probably going to be a conceptual list. You're not going to have a list of all tuples with a similarity attached to them, but find the first K of those items if you sort the list from most similar to least similar. And another way of doing it is to apply a threshold. So I'm not interested in images that are less than 0.9 similar to the sample image. Okay, so this kind of selection is quite different from the selections that we saw before. So to some extent, this is like inexact matching, and the previous examples are all exact matches. So we evaluate a where clause. If the clause evaluates to true for a tuple, it ends up in the result. If it evaluates to false for the tuple, it doesn't end up in the result. So that's a nice binary distinction. Here things are a little bit vaguer because we've got this range of similarity measures. All right, so how do we implement select efficiently? And that's what we're going to look at in the next few videos. One way you can do it is you can arrange the tuples so that certain groups of tuples are co-located, and that makes it easier to search for them. So one that we've already looked at is to sort the tuples. And then you can use binary search to find them faster than doing a linear scan. So if you like the base case, the worst case scenario is you simply scan all of the pages in the input. Sorting allows you to at least do, or having a sorted file allows you to at least do log 2 of the number of pages. The other physical arrangement strategy, obviously, is hashing, where you take a tuple, you compute a hash value for it, and that hash value becomes the page address where you store the tuple. So two tuples that have the same hash value possibly are similar and will end up in the same page. But more importantly, if you've got a query and you hash the value of the query, it'll give you a page, and if there is a matching tuple, it's guaranteed to be in the page indicated by the hash. Anyway, I'll have a look at how that works in a later video. And the other obvious strategy is to have extra information not in the file, so you can arrange the tuples however you like in the file, but have some auxiliary data structure that allows you to rapidly access the relevant tuples when a query is asked. So index files is one way to do that, and obviously we have things like B trees. And an alternative strategy is to use signatures, and we'll talk about them later. So we're going to assume a single input buffer. Having multiple input buffers doesn't really change these algorithms. They basically all assume that. The number of output, or the number of pages in the output, is going to be the same regardless of the method, because they're all attempting to do the same thing or produce the same result. So when we come to compare all of these, we're not going to include the cost of writing the final result effectively. If you've got multiple passes, as you do in some of these techniques, then sure, having more than one input buffer is useful, but not necessary to make the technique work. Alright, so that's a quick intro to selection, and we'll have a bunch more videos that talk about the different ways you can implement. Okay.